I'm Ebenezer Scrooge, and I'm here to talk about Chapter 7, Atomic Structure and Periodicity. So as you can see in Chapter 7, we cover an awful lot of things regarding what's going on within the atom. We're going to look a little bit at the past with like Bohr's model. We're going to be looking at electromagnetic radiation, the history of the periodic table, and so forth. Electromagnetic radiation is one way that the energy travels through space. Now, there are some characteristics of electromagnetic radiation that we have to look at. Well, there's wavelength. Okay, wavelength is how far is the distance between two waves. So if we're looking at a wave like this, well, how far is this compared to the next wave? See where my knuckles are, here and here. The distance could be very short, that'd be a short wavelength, or very long, like a very long wavelength. And we represent lambda as that. We also have the frequency, which is the number of waves, which you can also count as cycles in a second that will pass a given point in space. Okay, so waves, frequency. Frequency is represented by the letter V, not to be confused with velocity, which we have found elsewhere in chemistry, but that's a funny looking V there. Okay, that's a funny looking V there. 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 There you go. A higher frequency. I mentioned that's a funny looking V there. And I mentioned that several times. That's a higher frequency than if I just mentioned it one time. So that gives you an idea about frequency. Now speed, on the other hand, speed has to do with the speed of light. That's where c is. Now it is about close to 3 times 10 to the 8th meters per second, applying the Odell factor. Yes, we have to apply the Odell factor, otherwise this is for nothing. So we have a formula that the speed of light is equal to the wavelength times the frequency. That's the general idea. Okay, so let's look at an example of electromagnetic radiation. Red light has a wavelength of 700 nanometers. Whoa, new term here. Boop, 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 boop. What are nanometers? 1 nanometer is 1 times 10 to the minus 9th meters. So a nanometer is really, really tiny. We get to calculate the frequency. Well, if we look at the speed of light is equal to the frequency times the wavelength, we can go ahead and actually look at what's going on with the red light. How often does it go through? Well, the first thing we're going to need to do, we got to change those nanometers into meters. How can we do that? Well, that's where we can basically do our conversion system here, our dimensionalysis, if you will. 700 times 1 times 10 to the minus 9th meters for 1 nanometer. Notice how the nanometers will cancel out very nicely, and you get 7 times 10 to the minus 7th meters. So again, that's really stinking tiny. Now we can plug it into the frequency. If we know that the speed of light is equal to the frequency times the wavelength, then we can say the speed of light divided by the wavelength will give us the frequency, which is what we have here. And if you notice, I'm kind of bouncing around a little bit here. So we take the speed of light, 3 times 10 to the 8th meters per second. That's the fastest thing we know that travels, divided by the wavelength, which we notice how we converted it to meters from nanometers. Yeah, we needed to do that, and we end up getting 4.29 times 10 to the 14th per second, because the meters do cancel out. You say, well, wait a minute, what is about the idea about frequency? Well, remember, it's how many times something will happen in a second. In this case, when we're talking about waves, it's how many waves pass a point in 1 second. That's the idea behind it. So in this case here, for the red light, it has a frequency of 4.29 times 10 to the 14th per second. If you want to sit there and say waves per second, cycles per second, if that makes you feel better, but do not forget the Odell factor here. which we didn't, because if you notice, we have got 3 significant figures there. Yes, I do feel good about myself. All right, let's take a look at the next thing here. So when we look at the nature of waves, if we look at 1 second, we look at 1 second here, and if you notice here, the frequency, the unit of frequency is something called the Hertz, which was named after the guy who came up with the concept, Hertz. Now, this is not to be confused with Hertz Rent-A-Car or Hertz Donuts. You'll have to ask me later about Hertz Donuts, okay? Put Krispy Kremes to shame. Just saying. So here we have got a few, oops, let's go backwards. So here we have 3 different waves. We've got red, green, and blue. And if you notice here, for the frequency that's V1 is 4 cycles per second, which is 4 hertz. Okay, for the green, it's 8 cycles per second. So now actually the green is going twice as fast as the red. So I would say it's reasonable to say that the green probably packs more of a punch in terms of energy that's going through. Now, look at the blue. Yeah, just look at that blue, you know? Blue and gold, very awesome colors indeed. It's got my seal of approval. But if you notice, it says 16 cycles per second or 16 hertz. Now, if you look here, look at the lambda, look at the wavelength here, and you'll notice that, hey, the shorter the wavelength, the higher the frequency. Yeah, that's exactly it. Now, remember, if you get confused about something, you can always press stop or pause. You can always rewind it, okay? And that would work. All right, let's look at the classification of electromagnetic radiation. A lot of people think about electromagnetic radiation in terms of, and I'm moving my picture over here, a lot of people think about radiation, oh, I'm going to get radiated, I'm going to glow green, and I'm going to have issues, and It's one form of radiation. It's not the whole thing. Electromagnetic radiation covers a lot of things out there. Okay, so if you look on the diagram here, you'll notice that what we see as the rainbow, the visible wavelength, it's a very tiny part of the electromagnetic radiation spectrum. Okay, we have gamma rays, X-rays, ultraviolet, then we have the visible, the rainbow. Okay, VIB-GUR, violet, blue, green, yellow, orange, red. That's one way to memorize the order of the spectrum. Or Roy G. Biv, red, orange, yellow, green, blue, and violet. So VIB-GUR or Roy G. Biv. Take your pick. Then after that, you got infrared, microwaves, radio waves, which would throw in AM, FM, shortwave. And of course that gets to be fun because when all the hip trendy people out there sit there and go, Power 106, yeah! Well, that's the frequency that you can tune your radio to go and pick up, you know, Grandmaster C's latest hits. I'm just saying, okay? So down below, what you got here on the top, this is the individual wavelengths. And if you notice something, gamma rays are very short, very, very short wavelengths compared to when you're looking at AM radio, which is very long, long wavelengths. Kind of like Dory in Nemo. Yeah, okay. So this is the classification of electromagnetic radiation here. All right. So the idea, we have some very important concepts here. We have here the short wavelength, high frequency, and high energy. It packs more of a punch because you've got more waves that are coming at you, boom, 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 compared to, you know, if we were looking at long wavelength, small frequency, okay? it should be a shorter, well, yeah, a small frequency or low frequency, low energy, that kind of thing. Like, whoa, that's low energy, long wavelength. And here it's a lot shorter. Boom, 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 boom. Oh, man, this is too much. Okay, let's move on, shall we? Let's talk about the quantization of energy. Now, you're wondering, hey, behind Grandmaster C, there would be this dude named Planck. Now, here's the idea. An object can gain or lose energy by absorbing or emitting. So absorbing, you're soaking it up. Emitting is you're just giving it off. You're just giving it off. Kind of like free downloads from Grandmaster C. Ah! Oh, yeah. Now, it is the objects that they can lose or give off energy, it's in certain amounts called quanta. Okay? The energy of radiation is proportional to frequency. In other words, if you got low energy, you're not going to have a very high frequency. On the other hand, if you have a high frequency, boom, 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 you're going to have more energy. Maybe this is why AM radio waves won't kill you, because they have low frequency, low energy, but gamma radiation will. And it's not turning you big, mean, and green. That is the comics/movies. Moving on. So we have the energy is equal to Planck's constant, which is right there, times, well, the frequency. Yeah, the frequency. Okay, we're going to stop here for this little section, okay? And I'm hoping section 7.1 was beneficial to you. I know it was beneficial to me. All right, guys. This is Canu signing off.